So, welcome again to More Than C++ Testing with Catch2. So that's the image I was talking about. The reason I wanted you to see this, because you may actually be wondering what it is. And actually, all the links are at the end, but if you click through to the Flickr page where this comes from, the photographer actually has a little bit of a story about it. And he said that when he took the photo, it reminded him of a superhero catching a speeding bullet. And you can sort of see that there. What it is actually of is a handrail on a bridge somewhere in Canada, taken with a really narrow depth of field, so you get this nice blur effect. But yeah, I thought that was really fascinating, so I decided to keep it as my title slide. It's got nothing to do with catch or testing, really, other than the fact that it had catch in the name. But there you go. So because some of this material does get a little bit dry, it's actually brought to you with the help of classic programmer paintings. Now, if you haven't seen this is a really amazing Tumblr. It's just a collection of classic oil paintings with the title changed to something to do with software engineering. Some of them are really amusing. So I've just taken some of these paintings for my slides without the titles, so you'll have to read your own interpretation into it. And of course, with the help of Twitter, there's always a few applicable tweets. Not too many, just enough, I think. So okay, let's get started. And I actually wanted to kick off just by talking about testing in general. And I want to pose this question to you. Why is it that so many people don't write, well, first of all, tests at all? And I'm sure it doesn't include anyone in this room. And if it does, that's okay. Come to the right place. But I think we can include everyone if I ask the second part. Why do people write not enough tests? Because when was the last time you finished a project and you sat down and thought, yeah, I wrote just enough tests for that? I know I can't think of a time that I've done that. So if we know that we need to write more tests, but we don't, what is it that's stopping us? And it's not a trick question. I've put some common candidate answers up here. And the most obvious one is just simply that it seems like extra work. And one of our most endearing properties as programmers is that we're lazy. Why would we want to do extra work? And it's this idea that it seems unnecessary. So it leads into the second one, that we've probably already checked it manually somehow. Why would we want to test it again? That's extra work. We want to avoid extra work. The last one we don't hear quite so much these days. It used to be a bit more common that we've got other people that do the testing, but we still sometimes hear that. But I want to dig into this thing about it being extra work a little bit and ask, again, just to think hypothetically, if you're not writing tests, how do you know that your code does what you intended it to do? And the clue's up there. Again, it's not a trick question. We'll probably just run our application or service or whatever it is, maybe prod around with it a bit or click on something if it's a GUI. Whatever it is that will reproduce whatever it is we intended to do. I just check that it does it. Simple as that. Sometimes we may have to resort to stepping through with a debugger, but yeah, we do it manually, manual testing. And the thing about that is, for many of us, that's actually what got us into this in the first place. This idea that you can write something to make the computer do something, and then you can see that it actually did what you intended it to do. You get a buzz from that. You get the dopamine hit that takes you on to the next feature. So in a very real sense, manual testing can actually be quite fun, if you think of it that way, but with one really important caveat. It's only the first time you do that test. Because, really, we don't repeat these tests enough. Once you've actually tested that it does what you intended it to do, you move on to the next feature. In the process of writing that feature, of course, you may break something you've already done. Do we go back and test that if we're doing manual testing? And the chances are we don't, or we don't do it enough. Because, you know, let's be honest, it's tedious and it's repetitive, and we're not really cut out for that sort of thing. I mean, also, it's repetitive, you know, and it's tedious, and we get the idea. Like I say, we're not really cut out for that sort of, you know, tedious, repetitive task. But a computer is. It's what they're designed for. It's what they're great for. So when we're writing tests, that's what we're doing. We're offloading this work onto the computer to let it do what it's best at. It's going to save us time. So it's actually less work in the long run. So let's flip this around and ask the other question. Why should we write tests? And there's two parts to this, and it's worth considering both parts. The first reason we write them is to establish a correctness, to, like I say, to actually see that it's doing what you intended it to do. But once you achieve that, once you see your test passing, it flips into a different role. And that's a type of regression test to make sure that it continues to do what you intended it to do. There are different roles, and particularly if you're doing TDD, it's very important to know the difference because they actually have different value associated with them. Once you've actually got your test green, you move on to something else. Sometimes those tests, if they're very low-level tests, may actually start to become a hindrance if they're not tied up to your high-level requirements. And we're not going to dig too deep into that, but sometimes you have to delete tests. But then the other side to this, and I've touched on it already, is why should we write tests first? TDD. So we've already touched on the first part, which is sort of codifies our expected outcomes. So we had this idea of what we intend our code to do before we write it. That's the best time to write down that intention. While you're still in that designer's frame of mind. You actually got a different mental mode and you access a different mental resources when you're in that frame of mind. You lose a lot of that when you switch over to being an implementer and you're at the code face, writing the code. You get distracted by all the low-level details. You start following off different threads. The test will keep you honest. They'll actually stop you from doing things that you hadn't intended to do at the start. So that's really important. And also, and you may have heard the TDDers talk about this, that the tests exert a design pressure on your code or guide the design of your code. And what this means is TDD won't automatically make your code clean, but it will tell you when it's not. It will make it obvious, and it will make it hard to test code if you haven't adhered to certain design principles like separation of concerns or isolation and single responsibility, those sort of things, which are actually quite hard to keep on top of unless you've got tests there telling you when you're getting it wrong. And if you follow those signals, listen to your tests, then you can end up with cleaner code for actually less effort because you're doing it at the start when it's easier. So this is not a talk about that so much, so I'm not going to dig too much into it, but I wanted to give you some high-level principles. But I also wanted to look at the other side to this, which is that there's a very real cost to leaving bugs in your code, bugs that testing could help you to get rid of earlier. And in many cases, this can be an actual financial cost. And it can be entertaining just to look at some examples for a moment. So one of the very first examples of a software bug that had a real dollar amount associated with it was the Mariner 1 rocket, which was destroyed due to a code error. Now, in this case, it wasn't an error that could have been caught by a unit test because it was in the transcribing to punch cards. But nonetheless, we have a figure that we can put to it, which was $135 million in today's money. So that's quite a lot for just a single error. Sticking with rockets, slightly more recently, the Ariane 5 in 1996 self-destructed after an integer overflow. Worst part about this one is that code wasn't even meant to have been in that mission. It was left over from a previous mission. And that had a cost associated with it of $370 million. So creeping up. But it's not all rocket science. You may know who this guy is. This is Tony Hoare, who famously self-confessed to his billion-dollar mistake, which was the invention of the null pointer or null reference. Yep, he confessed to it. And it was him who estimated that it probably cost the industry something on the order of $1 billion. And this was some years ago already now, so probably all the more. Again, you couldn't catch this with a single unit test. It's a language feature. But how many tests have we had to write as a result of this? So, something to think about. As I say, the dollar amounts are creeping up, and it gets worse. So in 2002, the NIST released a study into the cost of software bugs. And there's a few choice quotes from that study. The full study is linked at the end. It starts off, software bugs are costing the US economy an estimated $59.5 billion each year. This is in 2002, just the US economy. Then it says improvements in testing could reduce this cost by about a third, or $22.5 billion. And then the general consensus seems to be that the current state of the art with respect to testing is poor and can be sufficiently improved. Now, this study is not without its critics. In fact, I'll also link to some critiques from the time at the end. There's a feeling that they had something to sell off the back of this. But I think it's clear that there's some really serious money involved in software bugs that we could be reducing by better testing. It's also interesting that this was in 2002, sort of at the start of the Agile revolution, when things like unit testing and TDD were starting to move into the mainstream. It could be argued that in the meantime, state of the art with respect to testing has actually improved. The question is, has it improved sufficiently? Now, the NIST, as far as I know, haven't done a follow-up study, but I did find one from 2013 from Cambridge University, and that put a figure of 312 billion, although that was globally. So really talking about huge amounts. But this is getting pretty heavy and serious. I think we need some cat pictures. So back on track, just to summarize this section. I think we all know that we need to write tests or more tests. The problem is it just seems like too much extra work to actually do it. So we first of all need to realize that it's going to be less work in the long run, and in some cases it may actually be less work in the short term, depending on how you work. So we just need to overcome this idea of it's extra work. But now we finally get to the subject at hand, because the implication of this is that our testing environment, particularly our test frameworks, should be as easy to set up and use as possible, and with minimum friction. And this was not the case when I started looking around about 7 years ago for a test framework for a project, and all the ones I trialed were just so much effort to set up and run. I was really demotivated. And it got me thinking, if I'm really motivated to test this project and it's so hard, what are people that are not quite so motivated going to feel? So that was one of my main motivations for writing Catch, to try and make it simpler. And I think it's achieved that. A lot of people tell me the same. So I think what we're going to do now is a quick demo to introduce you to Catch. So hopefully that will hold. Yep, good. Now, I've showed this at the beginning. I think the resolution has changed since. So that's a bit small now, isn't it? Let's increase the font size a bit more. How does that look at the back? Just take it up a little bit more. That should be fine. Okay. So I'm going to create a brand new project. This is in C-line, by the way. And we call it Hello Berlin. So I'm feeling imaginative today. All right, so we get, let's make that full screen. Just our usual, hello world, we'll get rid of that. So we've got a completely empty project now. So I'm just going to include, if I can spell it right, catch.hpp. And that's our first failing test, which I'll prove to you by trying to compile it, because we don't actually even have the header file. So first thing we need to do, and I didn't adequately prepare this, but let's grab that. In fact, I'll just move it straight into the project. Here we go. So we just got the single header file there. So Catch is distributed into a single header file. That should now compile, but it doesn't link. And the reason is, although it's a single header file, the part that defines main is defined separately. So if I write catch config main, if you define that before you include it, then it will generate main, and also all of the parts of the code that would normally be in CPP files will be compiled into this translation unit. So that will now build. And it's compiling the whole of Catch. That takes a few seconds. Here we go. And that is now a complete working application. If I run that, good. Doesn't do much, says no test ran, but it runs. Now we can start writing a test here, but that's going to take a while to compile each time. So what I'm going to do is create a new source file, start writing tests in there. So just include catch again. And now we can start a test case. We don't have to give it a name. We will in a moment, but we don't have to. In fact, let's start there. If you've used any other test frameworks, you're probably used to this idea that test names have to be couched as legal identifiers, usually as functional method names. And so you end up having to do all these contortions to work out what you're going to do with punctuation and spaces and things. Well, in catch, it's just a string. So you can say, you can put punctuation and spaces in. And you can probably see where I'm going with this. So let's write an assertion, which is by default require in catch. And I'm going to say 6 times 9, of course, is equal to 42. Let's run that. Yeah, a lot quicker to compile now. Let's have a look at the output. So we've got our test name, file and line number of the test, and of the assertion, the fact that it failed. We've got the assertion macro that we wrote, but then we have the breakdown of the left-hand side and the right-hand side. Now, if you've not seen this before, this is interesting because most frameworks will be required to rewrite our expression in like an assert equals or assert not equals or something like that. We just use natural C++ syntax here. And internally, it's used expression templates to decompose that expression and separate those things out and then put them back together to perform the comparison. That makes it much more natural. Now, it's failing. And having a look at this, I can't see anything wrong with my maths. I think all I'm missing is that this should be in base 13, of course. So let's change that. Now again, we don't have base 13 yet, so let's write that now. Now to save a bit of time, I've got a little snippet already prepared. And that returns a string, so let's change that as well. That should now build. There we go, run that, and we're good. So excellent. So before we move off this, let's just go to the console, and I'll run it from there. There we go. From there, we can do things like list the available tests, or we can get help. So we can see we've got quite a few options available to us. A lot of things we can do. We're not going to go into that now. But yeah, this is a fully featured test application. Okay, I'm going to stop the demo there. But in just a few minutes, we've actually introduced Catch into the project, started writing tests with it, seen a failing test, seen it pass, and even seen the output from the console. So let's switch mirroring back and go back to slides. Oop. Okay, that's where we left off. So previous versions of the talk I've done a few demos to demonstrate different features. I'm not going to do that now. What I'm going to do is just condense some of them into a few slides, some of the other features. Now, it's awkward without that there, but so here's a, no, it's not going to work, is it? There we go. Another test case. We can see our name there, but then there's a second argument, another string, it's optional, which is a list of tags in square brackets. So the test name itself must be unique within your test executable, but tags don't need to be unique. So if you tag many tests with the same tag, you can actually have sort of ad hoc suites that you can run. You can have multiple tags per test, so there's different cross-cutting suites. So that can be quite useful. There's also a number of special tags that have specific meaning to catch, which I'm not going to go into now, but we will touch on it a bit later. Basically, anything beginning with a symbol as a tag name is reserved for catch. But the bit I really want to draw your attention to in this example, if I can get this working again, here we are, is, well, we've got some requires at the top, but then we've got these sections. And this allows us to have a common setup and teardown code in a way that's a much more natural fit for C++. So again, if you've used other test frameworks, you're probably familiar with test fixtures, which are usually implemented as classes with test methods. And then I'll have special methods, or the constructor and destructor for setup and teardown, for common state between the tests. And actually, Catch does support that. But sections allow you to do the same thing in a much more powerful and natural way. But people who are new to Catch can be a little bit confused as to exactly how they work. So I'll run through it quickly now. So the assertions at the top will always execute. But then we'll hit the first section. Just here. In fact, I'll highlight it better here. We'll go into the first section and execute that. And then we'll skip over the remaining sections. So we'll come out. We'll then re-execute the whole test case again from the top. So again, we'll execute the first few lines. But then we'll skip over the first section because we've already seen that. We'll go into the second section. And then you notice that the second section has a nested inner section. Because that's the first one we've seen at that level, we go into that as well. So what we're doing is we're executing every leaf section effectively in isolation from the beginning of the test case. So all of our common setup code is just on the stack. So after that one, we'll execute the whole thing again, skip over the first two sections, and execute the third one. So that means that not only can you have multiple layers of setup, like we have here, but you see the whole thing on the stack, all on a single page rather than in different parts of your code. So it's a much more natural way of working. And you can take it further. There's a few macros that sort of map on top of sections to give you terms from the vocabulary of BDD. So we've got scenarios, which are really just test cases. And then inside you've got given, when, and then macros. And if you look at how this reads, we've got given an empty vector at the top, and then we actually have the empty vector in code right alongside it. Even verify that it is empty. Then we say, when it's made larger, and then you make it larger. Then the size and capacity go up. You verify that. And when it's made smaller again, make it smaller again, then the size goes down, but the capacity stays the same. And again, you verify those things. So it reads in a very natural way, and you actually have the code to match that alongside the natural language descriptions. And if one of these things fails, like the second one there, in the output, the test name that gets printed is just the full scenario description. That is the test name. So it's a really nice way to both structure your tests, but also report on them and maybe talk about it even with non-technical people. So time for Twitter again. Now, integration tests are important to Catch as well. It's not just for unit tests, but it is good to keep them separate. And one way that Catch has to help you with that is, remember I said about these special tags? So one of them is called hide, or can be abbreviated to dot. If you tag your test with dot, then they won't run by default if you just run the test executable. But if you add an extra tag like integration, or you can combine the two and say dot integration, then you can run everything tagged dot integration, and it would run just the integration tests. By default, it would just run the unit tests. So that can be a really convenient way to keep those things separate. So time for another oil painting. This one is actually not from the classic programmer paintings Tumblr, but it is a classic oil painting. It's obviously a Monet, one of his many water lilies. This is of the Japanese bridge. And this was painted over 100 years ago, 1899, I believe. Whereas this photo, the same bridge, was taken just this summer. It's my family in the middle of the bridge there. And the reason I'm showing you this photo is partly just as an excuse to get some of my holiday photos in, but mostly to demonstrate the passage of time. Because we've been looking at what Catch has been able to do all this time, and now I want to bring it up to date. Talk about what's new. Yeah, okay, it was a bit of a stretch, but... Before we get to Catch 2, there's actually a lot been happening just in Catch in general over the last year or so. Quite a few fairly big features have gone in. I'm not going to go into all of these in detail. There's a blog post on the special tags. There's a few of those now, like may fail, should fail, that sort of thing. Link to the blog post so you can catch up on that. I will talk a little bit more about matchers in a moment. We'll come back to that. Reporters. Catch has a modular reporting system. What you've seen so far is the console reporter. But there's also an XML reporter, JUnit reporter, Team City reporter, and there's a few more that have gone in the last year that are bundled with Catch. So it's worth checking those out if you use reporters. Listeners are similar. They actually use the same interface, but they're more for use within code, like for hooking events that will happen during the course of your test runs. And performance, the last one there. It's talking about both compile time and runtime performance. And right at the beginning, runtime performance is really a non-goal of Catch, because I saw it as a unit test framework. Why would it need to be high performance? But in times, people use it for different things. It's become actually much more important. So there's a lot of low-hanging fruit that we're working through to improve the runtime performance. Compile time performance has always been taken fairly seriously. That's why we have the separation of the main file and the other test files. But it seems that there's still room for improvement. So we've been working through optimizing compile times. Again, there's still more work to be done. This is ongoing. But that's already shown a lot of signs of improvement. So I was going to come back to matches. So let's have a look a little bit more closely there. Now, if you don't know what matches are, I'll explain briefly, but if you've ever used anything like Hamcrest, you should know exactly what they are. They're really just a way of writing custom composable assertions with a bit more sort of power and fine-tuning than the normal ones. So in this example, I've got a set of string matches. So this will allow you to, for example, test that a string contains another string or starts with or ends with. So you can see they all have the same assertion, so require that or check that. By the way, the difference between require and check is that require will terminate the test case if it fails, whereas check will carry on. And I said you can compose them as well. So here, for example, we're composing using the logical or and and operators. You can also use logical not, and you can use round brackets to group things. So you can actually get some really powerful composite matches using this technique. Particularly for strings, it works really well. As well as strings, there's some vector matches built in for checking a vector contains or is equal to another vector or contains a certain element. There will be more standard library matches going in, but that's all we have so far. But you can also extend with your own matches. Here's what you need to do. You need a class that derives from catch matcher base, templatized on whatever it is you want to match against. And then you override two virtual methods. You've got match, which takes your type, returns a bool, and describe, that returns a string just describing whatever it is the match is doing, and that will be reported in the event of a failure. You usually have a constructor to take any data you want to parameterize on. And that's it. It's pretty straightforward, and then you can use that in code. As well as the standard matches, assertions, we've now got check throws matches, which is why this one deals with exceptions. That will test that not only that your code throws, but that it throws a particular type, and it will then pass the exception itself onto your matcher for any further checking. So you can do quite a lot of checking of exception types now. So that brings us up to date on Catch 1. So we finally get to Catch 2. What's this all about? Main reason for the major version bump is that Catch 2 now relies on C++11. Some people were surprised this wasn't always the case. But Catch itself came out in 2010. It predates C++11. And of course, a lot of people have only been able to move on to it more recently. So I've held on to C++03 compatibility for a long time. And if you're not on C++11 yet, you can still get to Catch Classic, as we're now calling it, which is on a branch. But all the active development will be on Catch 2. So C++11 gives us quite a few things, mostly internal. It's able to really clean up a lot, particularly all the compiler compatibility checks and things. Ripped out at least 10% of the code just from that alone. Cleaned things up a lot. But it also enables some new things as well and lays the groundwork for the future. So the first little feature that came out of that was commas in assertions. This is the old problem of macros not being able to understand C++ code. So in particular, templates, the angle brackets with a comma inside, the macros think the comma means it's another argument for the macro. So that was always broken. But now we can rely on C++ 11, which has variadic macros. We just take everything you pass through the Assertion, just reassemble it on the other side, and it just works. Really nice. So a little thing, but it makes a difference. I already mentioned performance. This is ongoing. I even put a change in just this week to use a reusable string stream to avoid the constant cost of reconstructing one, as well as the compile time overhead of having to include I/O streams everywhere. New command line parser, which is called Clara. So I spun the command line parser out of Catch in version 1 to this library called Clara. For Catch 2, I've rewritten that from the ground up, not only for C++ 11, but also for a new design. I was going to give a demo of that, but I'm going to be doing a lightning talk on that on Saturday, so I'm going to save that for then. So do come along to that. So I won't say any more about Clara for now. And then we have a new name. This is the curious one. So one of the complaints about Catch originally was that it's very hard to search for things to do with Catch. Google or Stack Overflow, because not only is Catch a common C++ keyword, but it also comes up a lot in the context of testing. So got a double whammy there. So toyed with the idea of changing the name for a long time and looked at a completely different name to have a clean break. I liked the idea of Catfish for a while, but I didn't want to lose the momentum that had built up behind Catch. So I eventually decided on a more derivative name, which doesn't have all the advantages, but shouldn't have the disadvantages either. So I'm pleased to say that the new name for Catch is Catch2. So we'll see how much that helps, but I think it's mostly a branding exercise at the moment. And the last one on this list is micro benchmarks. I've got the experimental tag there because this is not really ready for production yet, but I deliberated for a long time over whether to include this in a test framework. I felt it was worth it in the end because it shares a lot of the same infrastructure. And so far, it hasn't really added a lot of overhead. But it's not complete, but it is already valuable. And in particular, I've been doing a lot of benchmarking recently and been finding a lot of the same problem of it taking a while to get up and running with some of the existing frameworks. So I thought I might do the same thing for micro benchmarks. We'll see where that goes. There's no documentation for it yet, but if you are interested in the self-test project, there's a test file for benchmarks. You can have a look in there. So that's what's in Catch 2 already. But I said this lays the groundwork for things in the future. There's quite a few things that have been put off for Catch 2 because this wasn't worth doing or wasn't practical to do before C++ 11. Most obvious one is threading. Without C++ 11 or any external dependencies, that's really hard. So deferred that. I've got a proof of concept that I just need to update, so that shouldn't take too much effort. And the idea there is that from within a test case, you should be able to launch threads yourself, but then raise assertions within the threads and not have any locking going on, and that will all just work, and just join at the end of the test case. So that should be coming soon. Then generators is something that has actually been in as proof of concept from the early days of Catch. The trouble is it never played nicely with sections because they both wanted to re-enter the test case, but they weren't talking to each other. So I put that off, but I did have a proof of concept that did work properly. It was just getting very noisy with C++ 03 syntax. So again, I deferred that, and I just need to reintegrate the work I'd already done. And generators are a form of data parameterization. So being able to run the same tests with different data inputs. Building on top of that, a slightly higher level feature is property-based testing, which is more of a formal way of doing this, where you have actually offers features for how it generates the data in the first place, and then boiling it down to the simplest possible failing case if it fails. So that will be coming too, but that's a bit bigger. As well as data parameterized tests, been a long outstanding request for type parameterized tests. So this is where you'll have a template and you want to run the same tests over it for different instantiations. Actually quite simple to do, but also quite simple to work around, so it's just been put off. I think it makes sense to do that at the same time. And then one more big feature that's been often requested is def tests. I think Google Test has this. And the idea here is that you want to test that your code terminates the process in a particular way. Of course, the only way to do that is to run out of process. That means Catch should be able to launch processes and monitor them, which is not rocket science, but it's not a trivial job to do portably. C++11 doesn't really help here, but because it's a bigger job, it's just been deferred. But that's still on the list as well. So that sort of brings us up to date with the past, present, and future of Catch. So really just remains for me to share that list of references that I mentioned. So on my website, I don't know if you can read it at the bottom, levelofIndirection.com, or if you prefer, extralevelofIndirection.com, /storage/catchrefs.html, or you can find me on Twitter, Phil_Nash, or of course on the JetBrains booth. And that's all I have to say for now, so thank you very much. And do we have any questions?
I didn't quite get what was the equivalent of fixture? I just didn't see how it looked like a fixture. Could we show up that slide maybe?
So the question was, how are the sections the equivalent of fixtures? So yeah, let me go back to the slide. So here, so at the top of this test case, we had this common code to create a vector and then actually do some tests on it. We could actually do some other things to prepare it. In the sections, of course, you have access to that vector. If you're doing this with a fixture, you would have a class that would have the vector as a member. You do any common setup and things in the constructor. And then each method would have access to that. So that's how they correspond. But sections go further because you can have subsections, and it's all held on the stack. Does that answer your question? Great. Another question.
When you have these sections, the benefit for me was less problems of naming, because you can reuse the same name and not V1, V2, V3. So it facilitates really the second, third, and so on test cases. The naming problem solved by that scoping.
So to repeat the question, or it wasn't really a question, it's an observation that another benefit of sections is in the naming, because each section is within another section of the test case. You can sort of follow on the name from the previous name. And in fact that, if I move forward a bit, is really borne out in the BDD example with the given, when, then. Oh, too far. Here we go. Because you can read the whole thing like a sentence as you cascade down the sections. So yeah, thank you for that. Yeah, Andrew.
Can it break the debugger on a failing require clause?
Excellent question, which I won't repeat because it was on the mic. Yes, you pass an option on the command line, -B, I think. Not supported on all compilers because it obviously is a little bit platform dependent, but certainly on Windows and Mac, I think somebody contributed a Linux version as well. I'm not sure if that's in. I should check that. By default, that will actually break exactly on the line that failed in your test code. What we found was that actually introduces quite a bit of compile time overhead. So when we've been optimizing that, we've experimented with a hash-defined catch fast compile, I think. If you have that defined, then instead that's compiled out and you'll break one level up in a function. So it's not quite as convenient, but if compile time is important, then we can do it both ways. So yeah, thanks for the question.
When Catch 2 will be released?
Sorry, repeat the question.
When Catch 2 will be released?
When will Catch 2 be released? Mm-hmm. Last week.
Okay.
Yeah, I've given this talk a few times, and I keep saying it's going to be released very soon, probably in the next week. Finally pushed it out last week. So, yeah, it was a very good question. I should have mentioned that.
And what about mocking? Do you have any... I'm here.
Sorry, I've lost you.
I'm here.
There you are.
So do you have any plans to create a mocking framework as well, not just a testing framework?
A mocking framework, did you say? Yeah. Last time I gave a catch talk here on this stage 3 years ago, I was asked about mocking frameworks, and I started talking about a couple of the mocking frameworks that I know work with Catch. And the author of one of them was in the audience, so I'm glad I said nice things about it. That was HippoMox. Does work quite nicely with Catch. So does Trompe, which is a newer test framework. So I generally recommend one of those two. I've got no plans to build mocking into Catch itself, partly because those frameworks do such a great job. In slightly different ways, you have to make slightly different trade-offs as well. And partly because not everyone needs it. In fact, I don't tend to do a lot of mocking myself. So I won't want to include a whole extra framework that most people don't need. But definitely check out those two.
I have a question. Actually, two small questions. First one, the tags in a scenario or in the test case, they are optional, you said, right? Like the vector or BDD or something, you said they are optional?
Sorry, I missed the middle bit of what you said.
The tags, like in a scenario in the first line, like vector, BDD, size, they are optional, you said, right? You can use them.
The tags are optional, yeah.
Mm-hmm. Okay.
So you don't have to provide them at all.
They can be anything you want, or is it more like, are they given from the framework? Or and how are they reflected in a test output in the end?
Okay, there's a few questions there. So tags, they can be anything you want, as long as they don't begin with a symbol, and they can be enclosed in square brackets. So obviously they can't contain a closing square bracket, because that will terminate the tag. Other than that, they can include spaces and punctuation within the tag. You can have as many as you like, up to limit of strings, I suppose. In the output, they don't appear directly in the output, but you can list the available tags. So you can see what's available and what test cases correspond to them. It's mostly for running a particular tag or set of tags.
The second question is, can you use something like timeouts on the tests as well? Can you say, in the command line, for example, can you set a timeout for the test?
No, but you can ask it to tell you what the times were for each test. So I would recommend, if you want to do that sort of thing, you do it externally, particularly in a continuous integration server like TeamCity. It's a good choice. That will typically show you the timings for individual runs and the trends over time. The reason I'm hesitant to put something like timeouts into the test framework itself is that makes it non-deterministic. That you may get tests that will fail sporadically or for external reasons. But if you do want to do that, then you can certainly do it externally, either by inspecting the times in the report or by timing the overall run. Okay, any others? Kevlin, by the way, is responsible for some of the biggest features in Catch. I stole them from him.
I lent them to Phil. I don't want them back. They're great. I love it. I love what Phil's done. Just on the timeouts, I was interested because timeouts are becoming the thing that's getting added to frameworks in a variety of languages. And although you say it introduces non-determinism, it does kind of solve the halting problem, which is non-trivial. But I was just wondering, when people are dealing with asynchronous code a variety of possibilities where we don't actually have a lot of control, or where there's going to be a propagation of potential timeouts and blocks, if that's something you might revisit.
So first of all, you heard it here first, that Kevlin Henny has solved the halting problem.
Yeah, the drinks aren't on me, though.
But whether I'd revisit the ability to actually assert on timeouts, I wouldn't rule it out. What I might do instead, though, is expose the timer that's built into Catch, report on the timer test, expose that in the public API so you can just do an assertion yourself at the end of the test case. So if this thing took more than X, then it fails.
That's kind of getting your toe into the water, just seeing how people use it. But, yeah, okay,
Yeah.
that's cool.
But for that. Okay, any others? Good. Well, you know where to find me, downstairs in the JetBrains booth. Thanks very much for your time.